All right. So this next little theorem, which we call the superposition principle, is a really, really important one in a lot of the solution techniques that we're going to be talking about. So let's suppose for a second that you have a total of k solutions for this homogeneous linear nth order DE. That's a mouthful, but we're going to be saying that a lot, so we're just kind of got to get used to it. I have an nth order solution, and I have k solutions, which I'm calling y1, y2, all the way up through yk, and it's important to note that this is homogeneous. Notice it's equal to 0. Suppose those are solutions on some interval I. Then we can show fairly easily, and we're going to do that right here, that any linear combination of those solutions, which remember is a function that's equal to a sum of multiples of those. So I have C1, C2, all the way through CK, constants that I'm multiplying to these functions, adding them together. That creates what we call a linear combination. Any linear combination of those k functions will always be another solution to this DE. Okay, so basically this is giving us a tool for constructing solutions out of known solutions. Okay, to prove this, it's fairly straightforward. We're going to use that operator notation. So again, remember, the left-hand side of this thing is an nth order linear DE, and we can define L to be the differential operator that we defined in the previous video, that when y is plugged into it, it gives us this left-hand side. So what that means is that for every single one of these solutions up here, I'm going to call them yi for short, where I can be 1 through k, L of I is equal to 0. Remember, this is just compact notation for this DE after plugging in one of the solutions. Okay. Now, if I construct a linear combination of those k solutions up here, which would look like this: C1, Y1 plus C2, Y2 plus something, all the stuff in between here, plus CK, YK, where all of those C's are just some arbitrary constant. Then I can use the linearity of L, which we talked about at the end of the last video. Every differential operator is linear, to bust this thing out into a sum of these kinds of terms here. So coming back over here, remember, this is how we define a linear operator. I defined it with two functions, where, again, it's almost like you can distribute the L into each term here and then pull the constants out like we have here. It's very easy to show, and I'm just not going to do that directly here, that this does not need to be restricted to a linear combination of only two functions. I can have any number of functions in my linear combination, and linearity would apply to that under this definition. So that's basically what we're seeing here. This, going from here to here, is using that linearity property. Now, the point of doing that is because now, instead of L of this big expression, I have L of y1, L of y2, L of yk, and all that stuff in between. Every single one of those is equal to 0. Because, again, we know that that each of these y's is a solution to the homogeneous equation given up here, and L of y equals 0 is just a representation for that homogeneous equation. So every one of those goes to 0. C1 times 0 plus C2 times 0 plus all of those C's times a 0 is just going to add up to 0 anyways. But that shows that this thing here is a solution to the homogeneous equation given up here, because I plugged that in to the operator that gives me this left-hand side, and I got 0 like I was supposed to get. Okay? So that establishes that important result. Now, what we would like to do is show that if you're good at selecting these functions here, that we can not only construct more solutions out of those, but we can in fact construct all possible solutions to this DE out of this finite set of solutions up here by using these linear combinations. We're going to work up to that result, but there's some conditions that need to be in place on these functions up here for that to work. And here's where we get into the topic of linear independence and linear dependence. Okay, so again, major topic in linear algebra. If you're following along and you're getting confused by all these linear algebra terms, even with my quick explanations, I do have on my YouTube channel a full linear algebra class in one of my playlists. If you want to, you can go and like look through some of those. Just be warned, when I talk about linear dependence and linear independence there, I'm talking about the more general case of working with vectors from a vector space. Functions are one type of vector, but the terminology I'm going to be using in those videos applies to a more general case. So that, be warned, I guess. Anyways, what is linear independence? Well, let's suppose that we have a set of functions, f1 of x, f2 of x, all the way up through fn of x. So n functions total in this case. We say that this set of functions is linearly independent if we form a linear combination of those, so c1 f1 of x plus c2 f2 of x plus yada 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 cn fn of x, and if we set that equal to 0, we would say that this set is linearly independent if this can only happen when all of the constants are equal to 0, when all of these constant coefficients are equal to 0. Obviously, that would work, right? If I plugged 0 in for C1, for C2, all the rest, I just get 0 plus 0 plus 0 plus 0, which equals 0. But we don't know in some arbitrary set of functions if there might be other choices of these C's that could also get us a 0 here. Linear independence says that only choosing 0 for each one of these constants can do this, and no other combination of constants will ever make this thing equal to 0. Okay, so that's what we call linear independence. If a set of functions is not linearly independent, then we say that it's linearly dependent. And what that would mean is that for that set of functions, I can find some set of constants, c1 through cn, not all of which are 0, such that this becomes true. Now, for linear dependence, it's okay if some of those constants are 0, but linear dependence just implies that not all of them are. So before I jump to this example up here, I realized I forgot to mention something here. We have some important consequences of our superposition principle. One is that if yi is any solution to a homogeneous linear nth order differential equation, so any one of these guys up here, any one of these solutions, then any constant multiple of any one of those solutions would also be a solution. And basically, let's just focus on yi, for example. If I know that, or y1, sorry, if y1 is a solution to this dE right here, and c1 is any constant, if I choose zeros for all of the other constants, c2 through ck, then all of those terms go away, and I get y equals c1 y1 as a solution to that dE. So every constant multiple of each one of these would have to be a solution as a consequence of that. In addition, if I chose zeros for all of my c's here, then I get y equals 0 after simplifying as one of my solutions. So what that's telling me is that every linear nth order homogeneous, with a 0 here, dE has the trivial solution, y equals 0. Okay? Back to this linear independence, linear dependence stuff. So here, we want to show that the following four functions are linear, the set is linearly independent. And again, linearly dependent. What that would mean is I have to find a way to form a linear combination of these four functions here, such that not all of the constants I use are 0, and yet the linear combination itself does come out to 0. Okay, so I have, my first function is sinh of x, hyperbolic sine. Then I have e to the x as another one, e to the negative x as my third function, and cosine of x as my fourth function. Okay, so here's what I want. I want to find some constant that I multiply sinh by, sinh of x, plus another constant that I can multiply e to the x2, plus some other constant that I can multiply e to the negative x2, plus some fourth constant that I can multiply to my cosine, such that the whole thing comes out to 0, and I would like to do this in such a way that not all of those constants are equal to 0. That would imply that this set is linearly dependent. Okay? In order to do this, we have to remember how sinh is defined. So remember, sinh is equal to, sinh of x is equal to 1/2 e to the x minus 1/2 e to the negative x. Right? Normally you'd write that as e to the x minus e to the negative x all over 2, but you notice it's the same thing, right? So what if I were to choose c1 to be 1? Okay? 1 times sinh of x, which can be written this way. 1/2 e to the x minus 1/2 e to the negative x. Okay, so remember that's C1 right there. All right. Now, I'm seeing some similarities in these terms with a couple of the functions I also have in this set that I'm looking at. Okay, so first of all, if I were to multiply that 1 in, I would have a 1/2 e to the negative x showing up as one of my terms here. To get all of this to go to 0, I would like to choose a constant for C2 such that the e to the x term I get from here cancels with the one that I have here. So for that, it would make sense to have C2 be negative 1/2. Okay, because now the 1/2 e to the x and this negative 1/2 e to the x will become a 0. Similarly, I have a negative 1/2 e to the negative x showing up here. If I chose a positive 1/2 for C3, that negative 1/2 e to the x and this positive 1/2 e to the negative x, those two terms, those are going to zero out also. So far, all of this adds up to 0. Finally, I'm left with this guy right here. The cosine of x seems to have no relationship to all of this, but let's just set C4 equal to 0. Okay? Remember, for linear dependence, it's okay if one or even multiple of those constants are 0. It just needs to be the case that not all of them are. This is clearly equal to 0, and so we have linear dependence here. Okay, so that set of functions is linearly dependent because of what we just did. All right, why do we care about this linear independence and linear dependence stuff? Well, the idea that we're kind of working towards, like I said before, is we're going to show that if you can find the right number of solutions, specific solutions to an nth order linear homogeneous DE like we have up here, and if we select them in a specific way, then all linear combinations of those functions turn out to be the general solution to this. Okay, now what conditions does it need to meet? Well, 2. We have to have a total of n functions here that we found as solutions, n corresponding to the order of the DE. So if it's an nth order DE, I need n of these. If it's a second order DE, I need 2 specific solutions. But not any n solutions will work. They have to form a linearly independent set to do what we need it to do. Now, what is the relevance of linear independence in this case? Well, if the set was linearly dependent, it turns out that that implies redundancy in our set. And here's what I mean when I say redundancy. Let's suppose, to begin with, we have a set of two functions, y1 and y2, and let's assume that those functions are linearly dependent. Then remember, by the definition that we came up with, that means that there exist constants, c1 and c2, not both of which are 0, because otherwise it'd be linearly independent, such that c1y1 plus c2y2 equals 0. Okay? Now, I don't know which one of those two or if both of them are non-zero, so we're just going to suppose that we're looking at the case where c1 is not equal to 0. Then I can solve for y1. y1 would equal this, negative c2 over c1 y2. It's very easy algebraically to solve that, and my assumption that c1 is not equal to 0 was necessary so that I could divide by c1 right here. Okay? By doing that, I'm showing that y1 is equal to a constant times y2, or in other words, y1 is a multiple of y2. That's what that's saying. Okay? Now, let's suppose that I wanted to construct from this set of 2 functions an infinite set of functions consisting of all linear combinations of these. Remember, linear combinations are all possible, or the set of all linear combinations would be the set of all functions of this type, a constant times y1 plus a constant times y2. Well, if I define y to be equal to some general linear combination like this, and if I use the fact that y1 is equal to this constant times y2, I have a substitution I can make. So over here, y equals a1, y1 plus a2, y2. And if I substitute this expression for the y2 here, now y2 is the only function showing up in that expression. If I factor the y2 out of both of these terms, I get negative a1 c2 over c1 plus a2 quantity times y2. Now this might look a little bit complicated, but remember all of this stuff in here, these are just constants. So this entire expression in parentheses here is just some constant. And that shows me that this general linear combination of the functions y1 and y2 is actually the same thing as just a multiple of y2, which means I don't need that first function y1 to describe the set that I'm trying to describe. I can throw it out and still have the same set of linear combinations that I would have had otherwise. Okay, I'm actually not going to talk you through this. I'm going to let you read through this, but this is following similar logic to show that in the event that you have n vectors instead of just 2, if that set is linearly dependent and I want to describe the set of all linear combinations of those n functions, it turns out that there's redundancy here, and I can actually get away with throwing one of those functions out of the set and still be able to describe the same larger set of linear combinations of all of them. Okay, there's redundancy there. So that's what the purpose of linear independence is it eliminates the redundancy. Every function in the set will be necessary. Okay? Now we've taken a set of functions and shown that it was linearly dependent. But how do you take a set of functions and show that it's linearly independent? There's more than one way to do it, but the tool that we're going to find the most useful here is something that we call the Wronskian. Okay, the Wronskian is a determinant, and again, I said at the beginning of the previous video that I'm going to assume that you know how to evaluate a determinant. I'm not going to explain that here. But let's define this thing. So let's suppose we have a set of n functions, f1 through fn, and let's suppose all of them are n minus 1 times differentiable. I can take derivatives of these guys all the way up to, at the very least, the n minus 1th derivative. Okay? The Wronskian, which we use this notation for, w of f1, f2, all the way through fn, remember these are functions in here, not numbers, they're functions, is equal to the determinant that has this form to it. So let's look at the rows of this determinant. The first row is just each entry in here. So each entry in this determinant is the function f1, the function f2, f3, f4, and so on all the way up to fn. The second row is the derivatives, the first derivatives of each one of these. So f1 prime, f2 prime, and so on. The third row would be all the second derivatives and so on and so forth until we get to the n minus 1th derivatives here at the end. This would be n rows and n columns, which means I can take the determinant of this thing. Okay? Now, we don't have enough background knowledge in this class to prove the result I'm going to mention right here, but you do if you've had linear algebra. And I believe, it's been a while since I've looked at it, but I believe in my linear algebra videos, I actually prove that the Wronskian does this. But it hinges on a lot of results that we developed previously in that class. So I'm only going to state the result and not prove it here. We can show that if you found a set of solutions, y1 through yn, of a homogeneous linear nth order dE, again that mouthful, on some interval I, and if that set of solutions is also that set of solutions will be linearly independent if and only if the Wronskian of those functions is non-zero for every value within that interval I. Okay? It also turns out that in the case of homogeneous linear nth order dEs, if these are solutions, you get an interesting dichotomy. So either the Wronskian will be equal to 0 for all values of x in an interval, or it will be equal to, or it will be not equal to 0 for all values of x in that interval I. You don't get an overlap. So again, if these are solutions to a homogeneous linear nth order dE, only in that case, this Wronskian, this determinant that we're talking about here, will either always equal 0 for anything I plug into it, or will never equal 0 for anything I plug into it, as long as I'm plugging in numbers from this interval I. Okay, in the case where the Wronskian is equal to 0 for all values of x that I can plug in for these functions here, we would say that it's identically 0 on that interval. Okay, so there's two cases that we get from this. If the Wronskian is not equal to 0 for every x in our interval, that these are solutions on which these are solutions to our DE, then this set is linearly independent. If it is equal to 0 for any value of x on that interval, then it's automatically going to be equal to 0 for all values of x in that interval, and we would say that this is linearly dependent in that case. Okay? So that's a lot of theory, a lot of kind of abstractness. Let's make it a little more concrete with an example. I made a mistake here. I wanted this to be a 1, not a 0. So this is, we want to determine whether the set of functions here, f of x equals 1, that's a constant function, g of x equals x, h of x equals e to the x, is that linearly independent or linearly dependent on the interval of all real numbers, okay? All three of these functions are defined on all real numbers, which is why this is the interval that we're using. Okay, let's construct our Wronskian. So the functions look like 1, x, and e to the x. Now remember, we're looking at a 3 by 3 determinant here where my first row are just these functions, 1, x, e to the x. My second row is the derivatives of each of these. So I take a derivative of 1 and I get 0. Derivative of x, that's 1. Derivative of e to the x is e to the x. Okay? Then I take second derivatives, which are the derivatives of each of these entries. 0, 0, e to the x. That would be my Wronskian. Okay? Now, if you remember how you evaluate determinants using cofactor expansion, I can expand this thing along any row or any column. If I expand along this first column here, I'm going to get 1 times the cofactor with these entries. 1 e to the x, 0 e to the x. Cofactor expansion would have me moving on to the next entry here and the next entry here. Both of those entries are zeros, and when I multiply them to the cofactors that I get in that expansion, everything else just goes to 0, and so this is all I need to consider. Okay, this is a 2 by 2 determinant. We evaluate these by multiplying my main diagonal entries and subtracting the product on this diagonal. 1 times e to the x is e to the x. Everything times 1 is just itself. I don't need to write that 1 anymore. E to the x minus 0. Okay, which is just e to the x. E to the x is not equal to 0 for any x. We know that about the exponential function. And so that means we're looking at case 1 up here. Our Wronskian is non-zero for every x in that interval that we're looking at here, the interval of all real numbers. That means that these functions are linearly independent. Which is great. Because that's really, when we're looking at solutions for these kinds of DEs, we want linear independence. That's the desirable outcome, okay? All right. Now, continuing on with this. If we have a homogeneous linear nth order differential equation, and if we've managed to identify n linearly independent solutions to that DE. Remember that DE will generally have infinitely many solutions. But if I've managed to find n of them, n being the same as the order of the DE, all on some interval I, and if all n of those form a linearly independent set, which we can check with the Wronskian now, then we would call that set a fundamental set of solutions to our DE on the interval I. Okay? And this theorem here is going to show what the relevance of that. Before we jump into this, I want to point something out here. This fundamental set of solutions is never going to be unique. Okay? There are plenty of different solutions. There's plenty of different sets of n solutions to any of these DEs that would form a linearly independent set. And any one of those could be considered a fundamental set of solutions. So it's important to note that this is not necessarily a unique set. Okay? But if we manage to find one, then this theorem tells us how we use that to come up with a general solution for a homogeneous linear nth order DE. I'm getting tired of saying that. So if we have a fundamental set of solutions for an nth order DE, a homogeneous linear nth order DE, on some interval I, then the set of all linear combinations, of those n solutions forms the general solution to that dE. So basically what that means is every solution to that homogeneous linear nth order dE is going to look like this, a linear combination of these guys here, okay? So here's an example where we use this. We're given a dE here, and again, we don't have any tools for being given a second order dE and then solving it. So we are given solutions. y1 equals cosine of the natural log of x, y2 equals sine of the natural log of x. We are told that these are solutions, and you can verify that if you want. Here's their interval of validity, 0 to infinity. I want to find the general solution to this dE. So first of all, notice that this is a linear second order homogeneous differential equation. Also, we had a theorem at the very beginning of the first video that said that in order to have a unique solution to IVPs, we need the leading coefficient here to be non-zero on the interval of validity, which it is, because 0 is not included here. But we're talking about a general solution anyway, so we don't need to get into IVPs. I want to show what the general solution to this would look like. I can do that by recognizing that this is a second order homogeneous linear dE, and I have two solutions. If these solutions happen to form a linearly independent set, then that would mean that we have a fundamental set of solutions. So I use the Wronskian to verify whether that's true or not. The Wronskian of these two functions, y1 and y2, is a 2 by 2 determinant in this case. So in this case, my top row will be cosine of the natural log of x, sine of the natural log of x, and then the second row will be the derivatives of each of these. What is the derivative of this? Well, chain rule on that gives me negative sine of the natural log of x over x. And over here, I'm going to get cosine of the natural log of x over x. Okay? Now, evaluating this determinant, I can do it the way that it's written, but it's a little difficult to work with. Just because these functions are a little more complicated than what I had in my previous case. So here's where we want to use that observation that we made over here. If this is non-zero, if the Wronskian is going to be 0, which would imply linear dependence, then it only needs to be 0 for some value of x in I. Let me back that up a second. Another consequence of this is if I can plug in, if I can pick a value of x and plug it into my functions in my Wronskian and then evaluate that determinant using the numbers that I get as a result instead of the functions, if that comes out to be not equal to 0, then I know that it wouldn't equal 0 for any value that I could plug in because it's an all or nothing kind of a thing. So here's what I mean by that. I'm going to evaluate my Wronskian, but at a value of x that's convenient. Specifically, I'm going to plug in 1. So y1 of 1, y2 of 1. What would that look like? Well, here, I'm plugging a 1 in for the x in this function. Natural log of 1 is 0. Cosine of 0 is 1. Okay? Natural log of 1 is 0. Sine of 0 is 0. Here, if this is equal to 0, then this numerator is equal to 0. I have negative 0 over 1, which is 0. In comparing this to this, I would have 1 over 1, which is 1. That determinant is very easy to evaluate. It's equal to 1, which is clearly not 0. So this is a linearly independent set. Okay? So what do I have now? I have two functions that I know are solutions to this dE because I'm told that they are, but I could verify that. And I've shown that they are linearly independent. Those two conditions, in light of this theorem, would say that the set of all linear combinations of these two functions form the general solution for this dE. So my general solution looks like y equals c1 cosine of natural log of x plus c2 sine of the natural log of x. And we just write it that way. You don't need to make any statement that says C1 and C2 are arbitrary constants or anything like that. We do stuff like this so much in this class that we just implicitly understand that C1 and C2 are just any constants that you want to plug in. Okay, I'm going to stop this video here, and maybe we can wrap everything up in the third video.